Actually one of the cooler videos, I think, because it's going to be an example of multiple regression. And so video 34 and video 35 will actually be an example of multiple regression. What I want to do in this video is show how multiple regression using methods, matrix methods, um, with all quantitative predictors. Video 35 will actually get into what if we have a categorical predictor such as gender, school district, whatever it may be, as one of our predictors. And things can change quite a bit when we run into that. So guys, anyway, here's what we're going to do. First thing I'm going to do here is we're going to use matrix methods. So use matrices, and we're going to open a data set. From the desktop, convert to matrices. We're going to calculate the coefficient estimates. We're going to calculate their standard errors. We're going to look at the fitted matrix. We're going to look at residuals. We're going to look at the hat matrix. We're going to look at identity matrix. We're going to look at we're just going to look at all sorts of cool stuff. After matrix methods, we're going to get into creating an ANOVA table. Along with creating an ANOVA table, I'm going to show you some nuances, sort of, the way ANOVA tables are often created, and it's kind of the default that we see in R. We're also going to get into R squared, adjusted R squared. We're going to get into the inference, so we're going to be looking at the test statistics, the p-values, the confidence intervals, and the final thing we'll do here is see how matrix methods can be used to make estimates on mean responses and predictions of new observations. So this is a jam-packed video. I say we're going to be going right around an hour. But it's one of the, it's kind of actually a cool video, because you think about it, what we're doing is we're kind of putting everything together and that we've talked about in the previous videos and making it happen. So it's kind of like you've gone to the store, you bought that new golf club, you're excited to get to the golf course and hit it. Well, we're getting ready to hit the golf club. We're getting ready to do some cool stuff. So, guys, one of the first things I want to do is show you what I have right here. And I have a data set, it's called IQ Read, and I'm going to open that up in Excel format. And what I'll do is I'll upload this video. It will be uploaded on Blackboard on the main page, and I'll call it, very creatively IQ Read. And so if we can maximize this, I want to give you an indication of what, let me make that bigger so you guys can see it. All right, what we've got here is some kind of, a semi-cool data set. And I can see, we're all math professors and math teachers and math instructors, and this kind of data set could clearly show up in something we would be asked to analyze for our students or possibly our school district. So right here, they've got a reading score, and I think this reading score was taken from the Metropolitan Achievement Test, and it's the reading score on that. LSS is kind of a cool measurement. What they did is they let kids of this age group pick out 8 books. And an independent observer, probably a teacher or maybe even a team of teachers, looked at the grade level of the book. So this is the average grade level of the 8 books that the student chose to read on their own. To my knowledge, they didn't know that they were that this was going to happen. So, for example, this student right here, the average grade level for the books that they chose. The 8 books they chose was 4, while this student right here, number 5, no, actually the 4th, chose books of higher reading level. Guys, here we have IQ. If you buy into that stuff, this column's for you. Personally, I've taken, I think, 11 IQ tests. I've never scored the same thing once, so who knows about IQs? EST is, this is a self-assessment. This is where the student estimated their own reading level. Guys, obviously gender is one of our first categorical variables. And over here, they actually got a school district. So apparently, these kids were randomly selected, or at least I hope they were random, from 4 different school districts. So the first video, this video 34 that I'm putting up right now, I'm only going to be concerned with these 3 variables. And the intent is going to be to predict read from LSS, IQ, and EST. So read is going to be the Y, and we're going to come in and choose our X's. This will be X1, X2, and X3. So we have a 3 predictor model. Now what I'm going to do is I'm going to shut this down, and I don't want to save. I've got it exactly the way I want it. And I've already got R up. So the first thing I've got to do here is I've got to get the data set open. It always helps me to get my working directory so I know exactly the form that I have. And then I want to set my working directory as the desktop. Now, I just being whatever, anal, whatever you want to call me, I always like to go back and check that the working directory is what I set it at. Now the next thing I want to do is I want to set this as my data, so I'm going to go read CSV. CSV stands for comma separated values, and I found on my computer, and I tried this out on my desktop as well, that I have more luck opening a CSV file on R than I do an XLS file. So gang, what I got here is I've got IQ read.csv. I encourage you to save it on your desktop as a CSV and open it the same way. Now, what I want to do now is I want to do data. No, I don't. Let's go data 1. And I want to do a data frame for data. So the data that I want to use here is going to be data 1. And when we do data frame on our data, this gives us a little bit extra advantage when we're trying to convert things into matrix form, or at least I think it does. Now, the very first thing I want to do, well, first thing I have to do is I have to attach data 1 so I can actually work with it. It's always easy to forget. And the easiest way to kind of check yourself on this is just try to take the mean of one of the variables. And if I had tried to do this before I attached data 1, I wouldn't be able to do that. Or at least I don't think I could. Once I attach it, that means I'm ready to do some to do some cool stuff. All right, so first thing I want to do is I want to create my X matrix. And recall, this is our design matrix. So guys, what I want to do here, first thing I want to do is set up a table of values. So if you remember, my first column in my design matrix has to be all ones. And if you look back at our data set, we have a 30 observations. So what I want to do here, first of all, is I want to go repeat integer, and I want to repeat ones 30 times. So now if I see my A's, I have 30 ones. All right, so that's really going to come in handy when I start setting up my matrix X. Guys, next thing I'm going to do is I'm just going to go for it. So I'm going to set up my matrix, and I want to bind together certain variables. So I'm going to do that with the C operation. So the first thing I want is A. The next thing I want is LSS. The next thing I want is IQ. And the next thing I want is EST. So I'm going to have a 3 predictor model. Hopefully you know by now that the next thing you're going to do is you're going to set up your rows. So I want my n rows to be 30. I want my number of columns to be equal to the ones, LSS, IQ, EST. So the number of columns is going to be always one more than our number of variables. And I've got to tell the program that I want by row to be false. I didn't enter my data by row. I actually entered it by column, because I've entered column, first column, second column, and so on. So guys, when I do that, I always like to just check it, and you can see I've got my matrix X, which works out really cool. Okay? Now, next thing I need to do is set up my Y matrix, and that's really easy to do, because my Y matrix will be just read. So in row will be equal to 30, and in column is equal to 1. And again, by row equals false. Guys, I've been told, I've never, believe it or not, I've never even tried it. I always put false and true in capital letters. I'm not sure if it works the other way or not. I'll tell you what, let's try it. Wow, that's crazy. Okay, well, we learned a valuable lesson, didn't we? C read. In row equal 30. In column equal 1. Alright, so guys, now we got our Y matrix, and life is good. So what I want to do first of all is I want to create my beta estimates. So I'm going to call that B. So guys, the first thing I have to do is I have to take the product of the X transpose X, but I have to take the inverse of that. So to take the inverse, I take solve. I want the transpose of X. Remember, we can't just do multiply. We multiply matrices. We have to do percentage sign times percentage sign and times X. So this part right here takes the X transpose times X and takes the inverse of it. Well, the next thing I need to do is to take the transpose of X again. And the next thing I need to do is take my Y matrix. So guys, now we can see that we have beta equal. Notice we have four values. So therefore our model is going to be, read can be predicted by taking the intercept, negative 26.55 plus 2.32 times, I forget, would we put LSS first? Yeah. Plus 0.47 times IQ plus 6.61 times EST. Now, interpretation. So the interpretation of LSS, the beta coefficient estimate is 2.32. So what we would say here is we would say controlling for IQ and EST, the predicted read increases 2.32 units with each unit increase in LSS. All right, gang, so what that tells you is imagine well, arithmetically in terms of the prediction, what we could do is we could hold IQ constant. Kid has IQ 105. So we want to let all kids of IQ 105 who estimated the reading level to be whatever it may be 6. Well, we can let LSS vary, and we could see that the predicted read would vary 2.32 units. Let's go another interpretation for IQ. Well, we would say controlling for LSS and EST. The predicted read increases 0.47 units with each unit increase in IQ. Guys, similarly for EST, I'm not going to write it, but it would be controlling for LSS and IQ. The predicted read increases 6.61 units with each unit increase in LSS. Now guys, this is really super important. Why is multiple regression so important to us? Because what it allows us to do is to partition out the variation in read that's attributed to these different things. Now we know, or we should know, that, let's say you buy into this whole IQ thing, and I do a little bit, but not as much as most people. But this LSS right here, the average level book that these students went over and selected out of the 8 books that they selected, in some way, shape, form, or fashion may or may not be attributed to their intellect, their aptitude. Well, what we've done here, and it would make sense, I don't know much about reading. I haven't studied reading scores and reading education data like I have math education. But the LSS, I would think that, more intelligent kids, higher aptitude kids would be tempted to go over to let's say you had free reigns at the bookmobile. I would think that higher IQ kids would be more likely day in, day out to choose higher level books. I don't know that, but that's actually what our model is actually testing here. So we could say that LSS, part of the variation in LSS is probably attributed to the kid's aptitude level, the kid's intelligence. Well, by us entering IQ into the model, we control for the variation in LSS that is attributed to the kid's IQ. So it's completely controlled for, not only arithmetically, but it's controlled for statistically. The EST stands for the predicted, the kid estimating their own reading level. Well, it may be argued that smarter kids are going to predict they have higher reading levels. I don't know that to be true, but that's what we do in statistics. We make hypotheses, we make educated claims, so we go out and test, gather our data, and we make those tests. So by doing that, if either one of these measures, LSS and EST, appear to be highly related to, and don't get too comfortable with that, because it actually turns out if we get 2 variables that are highly related, we get into something called multicollinearity, which is bad. So, but if we can think of the variation in LSS or EST or any of the combination of these, we want to put that variable in our model to control for it. Okay, the next thing we would want to do is we want to come in and get our standard errors for our betas. So next, we'll calculate the variance covariance matrix for our betas. Now, guys, you can't lose focus here and realize we have variance covariance matrices for betas. We have covariance covariance matrices for our errors and residuals. This is the one that we're going to use for our betas that are going to be helpful, actually necessary, when we actually get into the inference part where we create our test statistics. So guys, remember, this can be calculated by taking our mean square error times x transpose times our x, and raising that to the -1 power, taking the inverse of that. So you can't do that in R. I have to actually work this out. Guys, first of all, we'll calculate the mean square error, and the sum of squares for the error, which we'll need later, is calculated this way. The sum of the squares for the error is calculated by taking, so I'm going to take sum of squares error term here, and this is calculated using matrices as transpose of y times our y minus our transpose for our beta times our transpose for our x times our y. So our sum of squares error is going to be 8909.853. Now guys, remember our mean square error is found by taking the sum of squares error divided by our degrees of freedom. Now in this situation, our degrees of freedom are going to, for the error term, are going to be, well, this gets kind of complicated. Okay, I'll tell you what, let me get out of here and go back to this. Now this is complicated even for me. It depends on it depends on how we do this. Okay, if we're looking at our sum of squares for the error, for example, and in matrices form, now this is exactly what we did. Now, depending on how we set up our model, if we set this up, guys, I'm just trying to be thorough here, as having p minus 1 predictors. If we set it up this way, then our degrees of freedom for the error is going to be equal to n minus p. So in our situation here, we're going to have 30 minus, we have 3 predictors, so 3 predictors minus, so p minus 1 is equal to 3, so clearly p is going to be equal to 4. So we're going to have a degrees of freedom of 26. Now, a lot of books don't do that. And if all the books did that, I would stop right now. A lot of books, and this is really the way that I prefer it, set up our model as having k predictors. Well, in this situation, instead of n minus p, we're going to have n minus k minus 1. So, you know, that should make a lot of sense here. In our situation, we would have 30, and we would have minus 3 minus 1, and is going to give us 30 minus 4, which again is going to give us 26. You know what, I really don't care how you remember it. I'm going to be honest with you, I'm going to go back and forth, but the one thing that we all can agree on is that we have degrees of freedom 26. Now guys, I'm not going to make any major changes on you without telling you which one I'm using. And in both situations, most situations I'll probably use both. So guys, what I can do here is I'm going to come in and divide this by 26 to get my mean square error. So we can see that my mean square error here is 342.6867. Now, why do I need that? Well, guys, I need that for the standard error for my betas. So my standard error for my betas is going to be the mean square error times, now I want to put this in, so I need solve transpose x, shoot, yeah, is that right? Yes. Okay, that's fun. Well, I am completely confused why this isn't... Well, gang, I have no idea. I think what we're going to have to do is set it up this way. First thing I'll have to do is I'll have to look at this, and then I'll have to take my standard error for the betas, and I'll have to take the value 342 point, yeah, I think this is going to work, 67, and multiply it by my standard error. So standard error for the beta, yeah, that works. That's really strange that wouldn't multiply that out. Okay, all right, anyway. So remember that, make a note of it. Now, what's important here, if you look at the non-diagonal entries, this is the covariance between, for example, our second predictor, which would be LSS, and our first predictor. So this has a covariance of negative 41.94. Notice the covariance, you know, it's a lot like correlation, except correlation has to be from -1 and +1 because it's standardized. It takes the product of z-scores. Notice that the covariance does not. But what's important to us here is the variance on the diagonals. Now guys, remember, this gives the square of the standard errors. So to get the standard error for our intercept, we got to take the square root of 1067.794951. To take the standard error for LSS, we have to take the square root of 8.9865 9661. To find the standard error for IQ, we got to take the square root of, well, we got 0.08932 687. And to get the standard error for EST, we have to take the square root of the last diagonal, which is 9.842429. Yes. Now, kind of thinking ahead, where are we going to need the standard errors for our betas? Well, we're going to need those when we do get into our inference, where we calculate the test statistic, and we get into those things. Okay. Now, the next thing I want to do is I want to calculate our fitted values. In other words, our predicted values. So guys, remember our fitted values deal with the hat matrix. So the very first thing I'm going to want to do is create the hat matrix. And I'll tell you what, let me look something up here real quick. Okay, our hat matrix, which I'm going to be real creative and call it hat, is our x times the inverse of transpose x times x times our transpose x. You guys, our hat matrix is going to be a big old 30 by 30 matrix. Fun, fun, fun. Hopefully I don't require you to write anything like that out. And guys, remember our fitted matrix is our hat matrix times our y matrix. Okay? So I'm going to call it fitted. So this is going to be hat times y. So our fitted matrix gives us some cool stuff. Using our model, if we put in the x values, for example, for the first observation, this is going to I'll put it this way. Here in a second, I'm going to put this all in one data frame, one table, where we're going to see what we get there. Okay. Now, our residuals. And these are actually harder to do with. I'll tell you what. Let me write this out so you guys can be more thorough in your notes. The residual matrix. As I told you in video number 33, I think it was, requires the identity matrix. And it turns out that our residual matrix you know what, really? I guess the easiest way to get our residual matrix would just be to do residual and to do our observed y's minus our predicted y's. So our residual matrix would look like this.